a batch job caused disk I/O spikes, pushing etc. fsync latency to 500 ms. That triggered Raft leader election failures, making the API server unable to write state and bringing the entire cluster down. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Kubernetes architecture. Kubernetes architecture is a distributed system where a control plane manages a fleet of worker nodes. You declare desired state via YAML, and the system reconciles toward it. The control plane makes all scheduling and reconciliation decisions, while nodes are relatively dumb executors. The control plane makes global decisions. The API server is the front end, all communication goes through it. It validates and persists resources to etc. and exposes a watch API. The scheduler watches for unscheduled pods and assigns them to nodes. The controller manager bundles multiple controllers like node controller and replica set controller. Here's a set of commands to check the health of core control plane components. You can verify API server health, list etc. members, check leaders for scheduler and controller manager, and inspect pod health. When you run kubectl apply, a chain of events propagates through the control plane to the target node. The API server authenticates, authorizes, passes through admission controllers, then persists the object into etc. The watch mechanism notifies controllers, which create dependent resources, and finally the scheduler assigns the pod to a node. A node is a worker machine where containers run. The kubelet receives pod specs and ensures containers are running. It talks to the container runtime via CRI. kubeproxy maintains network rules for services. The CNI plugin configures pod networking. Here are commands to deeply inspect a node's status. You can check node conditions, allocatable resources, kubelet logs, container runtime, and kubeproxy iptables rules. Etc. is a distributed, consistent key-value store that powers Kubernetes. It uses the Raft consensus algorithm to achieve strong consistency. All cluster state is stored in etc. The key insight: etc. is a replicated log, not a traditional database. Performance heavily depends on disk I/O latency for fsync operations. Here are commands to check etc. health and performance. You can check endpoint health, member list, fsync duration, database size, and take a backup snapshot. The Kubernetes scheduler assigns unscheduled pods to appropriate nodes via a two-phase pipeline, filtering and scoring. In filtering, nodes that meet hard constraints are selected. In scoring, feasible nodes are ranked. The node with the highest score gets the pod. If no node passes filtering, the pod remains pending. The article mentions Raft leader elections, but doesn't explain quorum. With 3 etc. members, you need at least 2 for a quorum. Losing 2 members means the cluster cannot accept writes. Always run an odd number of members, 3 or 5, to avoid split-brain scenarios. The article warns about fsync latency, but doesn't show how to measure it. Use ekgictl to check endpoint status and disk metrics. Run this on an etc. node to see actual fsync durations. The article mentions pod preemption, but omits that it can take up to 30 seconds due to graceful eviction. For latency-sensitive workloads, design priority classes with realistic timeout expectations and consider using preemption policy. Never for critical pods. The article touches on CoreDNS but doesn't stress resource limits. Under heavy query load, CoreDNS can crash if memory limits are too low. Set requests and limits based on cluster size. For large clusters, deploy node local DNS cache to reduce load. Here are commands to debug scheduler behavior. You can check scheduler logs, pending pod events, node taints and resources, and scheduler queue depth metrics. Kubernetes assumes a flat network where every pod can communicate with every other pod without NAT. This is achieved through the Container Network Interface, CNI plugin. Each pod gets its own IP address. Services abstract pod IPs and provide stable virtual IPs. kubeproxy watches services and programs iptables or IPVS rules. Here are commands to debug pod networking. You can check pod IP, verify connectivity between pods, check service endpoints, kubeproxy rules, and DNS resolution. Two widely used CNI plugins are Calico and Flannel. Calico uses pure Layer 3 routing with BGP, eliminating encapsulation overhead, and supports rich network policies. Flannel uses an overlay network, VXLAN, and is simpler to deploy. For production clusters requiring network policies, Calico is recommended. For small dev/test clusters, Flannel suffices. Here are commands to verify node component versions including kubelet, container runtime, kubeproxy, CNI plugin, and IPVS kernel modules. The API server is the front end of the control plane and the only component that directly interacts with etc. Every kubectl command, controller watch, and component communication goes through it. Admission webhooks add latency to every API request. The watch cache can become inconsistent on large clusters, causing cascading relist storms. Here are commands to check API server metrics including request counts, admission webhook latencies, in-flight requests, and watch cache performance. This is the same issue we highlighted at the start. Here's exactly why that happened. A co-located logging agent on the same node as etc. caused shared SSD contention. This led to etc. disk write latency spiking to 500 ms, which triggered Raft leader election failures. The API server, which depends on etc., became unresponsive. The fix was to dedicate fast NVMe SSDs to etc., isolate it from write-heavy workloads like logging agents, and set a monitoring alert for fsync latency above 10 ms. Additionally, regular defragmentation using ekdectl helps maintain performance. This resolved the incident and prevents recurrence. Never co-locate etc. with write-heavy workloads like logging agents. The shared disk I/O causes fsync latency spikes, triggering leader elections and cluster instability. A slow admission webhook that takes 5 seconds to respond adds that delay to every write to that resource type. Monitor the metric and set timeouts to avoid stalling the control plane. If writes exceed the watch cache capacity, clients get two old resource version errors and must relist all resources. This can cascade into a thundering herd problem. Increase watch cache sizes or reduce watch concurrency. To diagnose issues, check etc. fsync latency, admission webhook duration, scheduler queue depth, and describe pending pods. These metrics help pinpoint the bottleneck. Let's run through some common interview questions. What is etc's role in Kubernetes? Etc is the consistent key value store that holds all cluster state, using Raft for consensus. How does the scheduler assign pods? Two-phase pipeline, filtering hard constraints and scoring ranks feasible nodes. What happens when etc disk latency spikes? Leader elections, API server unresponsive, control plane stalls. And a few frequently asked questions. Why is etc fsync latency important? It determines cluster responsiveness. Above 10 ms triggers leader elections. What is the difference between Calico and Flannel? Calico uses BGP for routing and supports policies. Flannel uses VXLAN overlay and is simpler. How can I debug a pending pod? Use kubectl describe pod to see scheduler events and check node resources. Key takeaways: etc is the single point of failure in Kubernetes architecture. Monitor its fsync latency and keep it under 10 ms. Admission webhooks can become bottlenecks. Always run etc on dedicated, low-latency storage. Ready to go deeper? Up next, Kubernetes network policies, then service mesh, then introduction to CI/CD. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.